Hello everyone, isn't it nice to be outside again? Anyway, look, before we start this video, I have to tell you that my sponsors have said that I've got to make them a bit more professional. I'm not telling you who my sponsors are, but I'll give you a clue if you like. Anyway, I thought to make it more professional, I'd do what people like Dr. Cox and David Attenborough do. I'd actually go all around the world looking for Fizziks. So, here we go. There's Fizziks here in the Sahara. It's so hot, the temperature is so high and the molecules are moving very fast. We've come here to the Himalayas where it's so cold the molecules are moving really slowly. I've come to Boston in Massachusetts to see the biggest Van de Graaff machine in the world. It's huge. There's a person in there, look, just in there. Yeah, with the Great Barrier Reef. Look at it. It's really pretty, isn't it? And the physics here. Colours are different wavelengths. Well, I've just got back from my travels and it was actually pretty tiring. Let's just go in the house. Very tired. I hope it's made it look a bit more professional for you, but I mean, probably it hasn't really actually done much for my carbon footprint. Well, as you can see. Well, today's talk is all about forces. Now, you could make forces actually very boring by saying forces are pushes or pulls. But let's try and make it a little bit more interesting. There are three types of force. There is the police force, the Royal Air Force, or indeed pushes and pulls. There are three main effects of forces, and our friend little Mr. Fizz is going to help us to see what these three effects are. There's a force which can cause a change of position or speed. Or a force can change the shape of something. Or indeed a force can change the size of something. There, did you get the idea of that? Good, hope so. Sorry about that. Right, well I'll just let the balloon down and we'll carry on. Before we go on with forces, we need to sort something out. So here's a question for you. Which is lighter, hydrogen or air? And the similar question, which is heavier, lead or polystyrene? Now, give you a pause for thought. Some of you may have said that hydrogen is lighter than air, and some of you may have said that lead is heavier than polystyrene, but it depends how much we've got, isn't it? If I've got that much lead and that much polystyrene, then the polystyrene's heavier. So heavier and lighter is the wrong word. We need to talk about density. Now, here's all about density. That is a bag of sugar, as you can probably see, and the mass of that sugar is 1 kilogram, okay? 1 kilogram sugar. So mass is the amount of stuff. There's a kilogram of stuff in that bag. We also need to talk about volume. Now, volume is measured either in cubic centimetres, or we say centimetres cubed, or cubic metres. Now, that's about a centimetre. So a cubic centimetre is a bit smaller than a sugar cube. It's a bit small, okay? That's a cubic centimetre. In terms of metres, I don't use this as a rule. That's a metre rule. So if we had a box which is that size, by that size, by the same towards you, that's quite a big box. That's a metre cubed, a cubic metre. It's about the same size as those bags you see where people have soil delivered to their house or something like that, or sand. So that's a cubic metre. Now that is volume. It's the amount of space that something takes up. Density is what compares the mass of things to the same volume. So for example, the density of water is 1 gram per centimetre cubed. So if you had that much water, it would have a mass of 1 gram. Or if you make that into big units, it's 1,000 kilograms for a metre cubed. Now that's quite a lot. So 1,000 kilograms is a tonne. And so water is actually quite dense, isn't it, when you think of it in that way. Beware, all of you who've got an old house and decide to have a waterbed, it comes out very heavy. So that's density. Now, density is something that an old chap a long time ago called Archie knew all about. Archimedes. And Archimedes knew all about density because he worked it out, didn't he? Actually, I bet his mum knew quite a bit about it as well. Clearly these photographs were not taken at the same year. That's Mrs. Medes, that's Archie. Now, she probably said something like, when he probably said, "Mum, I'm just going up to have a bath." And she said something like, "All right, well, don't fill it too full because I'm fed up with you splopping water all over the floor with your displacement." Anyway, Archimedes did indeed go and have his bath. And as you all know the story, whilst he's in the bath, he shouted out, "Eureka!" And that means in Greek, "I found it." And I think he was talking about the soap, because you know how difficult it is. And he ran down the street naked, shouting, "Eureka, Eureka, Eureka!" And all the Greeks shouted out, "You don't smell so good yourself." But basically it was all about density. Now, I wonder what you think your density might be. You might be very dense, but you might not be. Now, how does your density compare to water, for example? Well, if you breathe in, you float in water, and if you breathe out, you sink. So your average density is about the same as water. Interesting, eh? Same as a submarine. Now, this is a cross-section of a submarine, and that's a happy section of a submarine. And a submarine is made of steel, but it's also got lots of air in it. So we're talking about its average density. On the side of the submarine are tanks. And if the tanks are filled with air, it's like you breathing in water, and the average density is less than water, so it floats. If it wants to sink, it fills these with water, so it's all heavier, and its average density is more than water, so it sinks. There, all about density. One of the principles of Archimedes was about flotation, and he said that floating objects displace their own weight of water. I can show you that with diagrams. So, let this be water. Water's always got lines on it, hasn't it? Here is water with a ship in it. Here, oh, don't forget the lines for the water. Here is water. If I was able to magically take the ship out, and here is a bit of water that's come from there. Okay, so if I was to put this water in here and it fitted exactly, it would look like that. The bit of water, which is there, wouldn't go up or down. Therefore, the weight of that water must have an equal and opposite force pushing upwards from the water itself. Well, there's no difference in that water there than this water here, and so therefore there's an upwards force equal to W. But the ship isn't jumping up and down or sinking underwater, so therefore the ship also must have the same weight. So a floating object displaces its own weight of water. That's good old Archimedes for you. This is a lift lock near Peterborough, and it takes boats either up or down from one canal level to the other canal level, and it's nicely counterbalanced so that it doesn't take much energy to actually move it, because both sides are nicely balanced. Now, because of what Archimedes said, it wouldn't actually matter if one of the locks was completely full of ships and the other one was completely empty, because the weight of the water that the ships have displaced is equal to the weight of the ships themselves, and so therefore it would still be balanced no matter whether the lock is full or empty. Now we'll talk about weight. So once again, what's the weight of this? I hear some of you say 1 kilogram, 0 point. I hear some of you say 1 kilo, minus 1 point, because kilo just means 1,000. If you went to the butcher's and say, can I have a kilo of sausages, they might give you a kilometre of sausages. Kilo means 1,000, should say kilogram. Anyway, we physicists let you get away with calling the weight of that 1 kilogram, but that's not true, because weight is a force, and force is measured in a unit called the Newton. How appropriate. And something more appropriate, what roughly is the weight of 1 Newton? The weight of an apple, a small apple. A mass of 100 grams has a weight of 1 Newton. So actually, a mass of a kilogram, 1,000 grams, has a weight of 10 newtons. That weighs 10 newtons. Now I know we don't use newtons very often, and again, if we went down to Wilks's and said, can I have 10 newtons of sausages, he'd probably clip me around the ear and tell me to clear off. However, that is what weight is measured in. It's a force. Weight is defined as the force due to gravity. So that only weighs 1 Newton on Earth. If we took it to the moon, it would have the same mass, it's got the same amount of stuff, but it would be lighter. It would only weigh 1/6 of a Newton, because the gravity on the moon is 1/6. And if we took it to deep remote space, it's got the same mass, it would still be 100 grams, but it would have no weight at all. I put it there, it would just stay there. It would be weightless. So the weight is the force of gravity, but mass is the amount of stuff. So as far as gravity is concerned, that gives us our weight. And if we're on the moon, you'd only weigh 1/6 of what you weigh here. Wouldn't that be nice? That's why moon men are always like this, because they're so much lighter. You didn't know I had so light on my feet, did you? Well, look, light on my feet. Now we all know that Sir Isaac Newton was famous for the apple, and in 1687, I think it was, quick check, yes it was, when he was aged 44, he wrote down properly Newton's laws of motion, which some of you know a bit about. Now, here we go. Newton's first law says that an object will stay at rest or carry on in a straight line at a constant speed unless there's a net force acting on it, a resultant force, a net force. So let's just test it. Yep, it certainly stays still if there's no net force. There are two forces, there's a weight and the push from my hand, but they're equal, so it's not doing anything. We can't test if it goes in a straight line because we've got gravity here. You could only do that in deep remote space. Newton's second law is pretty much the same as the first law. It basically says if there is a net force, it will accelerate. Just like that. We've probably got a bruise on it now. So a force gives an acceleration, a balance of forces gives no acceleration. That's basically Newton's first and second law put together. And Newton's third law, you probably all know, for every force there's an equal and opposite reaction force. So just like I am being pulled down by the earth, I'm actually pulling up on the earth as well. And that's Newton's third law. Now let's just have those written down. So here is a summary of Newton's laws, and here is a wintery. Now let's just look at how those forces are involved with things like cars and aeroplanes and so on. Okay, here's how it works. Now let's look at the forces on this wonderful car. Do you know, it's just like my first ever car. Ah, a traction avant Citroën Light 15. Now, first question is, what force actually drives the car forwards? Where does that force act? You've got to think about this, see if you can get it right. I'll give you a few seconds. Probably a lot of you are saying, well, from the engine or from the gearbox or from the axle. Actually, no, it's from the tyres. Because as the tyres are rotating in this direction, they're trying to push the road back, and so the equal and opposite reaction force is the road pushing on the tyres. And because the road doesn't really move because it's so heavy compared to the car goes forwards. And if you don't believe that, try doing it on ice where you haven't got any friction and so therefore it doesn't move. Right, well, let's look at the overall forces on the car. And I'm going to represent the driving force by just an arrow coming out of the front there. So what we're going to do is we're going to start off and we've got a big driving force pushing the car forwards. And as we go faster, we start to get air resistance or drag. The air's got to be pushed out the way, and so we get a bit of air resistance. And we go faster and faster still, and we get more air resistance. And we go faster and faster still, and we get more air resistance until there's so much air resistance it's equal to the force that's driving it forwards. And when those two forces are equal, then there is no more acceleration, or it goes at constant speed. So if you're going at a constant speed, the force equals the drag. If the force is greater than the drag, it will accelerate. If the force is less than the drag, it will decelerate. And if the force is at its absolute maximum, so the engine's going as hard as it possibly can, and the drag is equal to that force, then we call that the top speed. Now, an aeroplane is pretty much like a three-dimensional car, really. To start with, we've got a forwards force. Now, where do we get that from? As the engines push back on the air and exhaust, so the air pushes forwards on the engines. So all four of those engines put together add up to what we call the thrust, and we'll represent it like that, a big arrow like that, and I put TH for thrust. There's lots and lots of air resistance, and we call that the drag because it's acting backwards. So if the thrust equals the drag, then the forces are balanced, and so it's not going to speed up or slow down. And constant speed, thrust equals drag. Now, we've got three dimensions to think about here, so we've also got the weight of the aircraft, so W acting downwards. But of course it's got to stay up there, so we get the lift from the wings. There is the lift. And if the lift equals the weight, then it's not going to accelerate up or down. It just carries on doing what it's doing. So if it's going at a constant straight and level flight, the lift equals the weight, the thrust equals the drag. What happens if you actually decrease the thrust on the engines a little bit? If the thrust becomes a bit less than the drag, it will slow down. Slowing down means less lift, say it properly, and therefore it will actually go down, not just go down, but accelerate down. And that's how the aeroplane works. Now, you probably also want to know how come the wing actually manages to keep the aeroplane up. So, here is a picture of an aerofoil section. So, a cross section through the wing looks something like that. Bing bong. The Bernoulli effect. When air flows past a surface, the pressure lowers. I could show you that with a bit of paper. It's a principle of flight. Watch. Air pressure same on both sides. Blow over the top. The pressure lowers, it goes up. Clever, eh? And what happens is the air comes along like this. Some of it goes underneath and some of it goes on top. But look, the bit that goes on top has got a bigger distance to go than the bit underneath, which means it's going faster. And if it's going faster, we've got less pressure on top than there is underneath. So therefore an overall pressure upwards, which pushes the wing upwards. Now you often see pictures like this with these, they're called streamlines, the air going off like this, but that's not right. It's actually got to go downwards after it's been across the wing, because as the wing pushes the air downwards, the air pushes the wing upwards. And talking about aeroplanes, something quite interesting. Pretend this is the wingtip here, so there's the top and the bottom of the wing, and we know that there's less pressure on top of the wing than there is underneath it. So at the end, that means that air will flow from the higher pressure to the lower pressure, and as the wing goes along, it means it makes a swirl, a vortex of air. Now that is energy, and you're losing energy from the aeroplane by making the air do that. And so that's why lots of aeroplanes now have a little bit sticking up on the wingtip to reduce the effect of that. But here's something else interesting. Birds do it. So imagine a goose flying along and it's creating this vortex. What happens is goose number 2 likes to fly in the bit of air that's going up because it doesn't have to work so hard, and so on and so on and so on. And that's why geese and ducks fly in a V formation. The one at the front works harder than the rest. And every now and then they actually change leaders. Isn't that interesting? Physics is. Now, how about this? This is a Hawk aircraft like the Red Arrows fly. In fact, it is a Red Arrows aeroplane. Think of the wind coming along here relative to the aeroplane. Hey, does that remind you a bit of the aerofoil? You actually do get some lift from the shape of the fuselage itself, and because it's shaped like a wing. And by the way, look, I had a go in one of those once. It was great fun. Well, look at Lewis's car. It's a bit the same, isn't it? Some air goes underneath the car. Some air goes over the top of the car. So therefore we have lift. It behaves like a wing, which is why we've got these bits on the front and that bit on the back, which are actually wings, but they're upside down wings. So they give, as it were, a lift downwards, a force downwards, to keep the car on the road. How about that? Now, here's how the forces work on a free fall parachutist. Here's our intrepid Mr. Fizziks doing a free fall parachute. Just imagine this is the moment he stepped out of the aeroplane. The only force acting on him is his weight. But because he's got a force, he will accelerate downwards, as we all know. And if he accelerates downwards, then he got a bit of air resistance. But the weight's bigger than the air resistance, so he's still accelerating downwards, and so therefore he goes faster, so he gets more air resistance, and so on, until the air resistance is the same value as the weight. Once those forces are balanced, he will no longer accelerate. He goes down at a constant speed. We call it the terminal velocity, and that's probably because if he doesn't open his parachute, it's a bit terminal. So there he is, falling down at a constant speed, which is about 120 miles an hour for someone in that sort of position. Anyway, what happens then is he opens his parachute. Okay? And you all know from having watched the films that the moment he opens his parachute, he shoots upwards, doesn't he? No, he doesn't. That's because the cameraman is still going down fast. And so it looks relative to us that he's going upwards. So what happens is this. Okay, here he is, this now. There he is, hanging on like anything. And here's his parachute. Now, the moment the parachute opens, he's got the weight acting downwards as before, but he's got a huge air resistance. So a very big drag or air resistance. And the air resistance is greater than the weight, and so therefore he will decelerate. And that happens until you get to the situation where the air resistance is equal to the weight, in which case he goes down at a constant speed. But of course it's a lot slower because he decelerated, and so he's happy about that until he lands. We like to use machines, And by definition, a machine is a device that enables us to do work more easily. And if we're doing work, the amount of work we do depends on the force we use and also how far we push it. It's actually force times distance. That's how we calculate work, but it doesn't matter about that. And if you're doing work, you're losing energy. So the less energy you can lose, the better. Now, machines are devices which enable us to do work more easily. That means you can either use a smaller force or you can actually make longer over doing what you're doing. So, for example, supposing you've got to load something into the back of a lorry, a big box. It's very heavy to lift it up directly against gravity and plonk it on there. So what you can do is use a slope. Now a slope is properly called an inclined plane, and although you have to push it for a bigger distance than that, you need less force, and so therefore even a plank, an inclined plane, is a machine. Another one you might like is this. If you've got a weight, let's have 100 newtons on a string, and if you want to pull it up, you need 100 newtons. But supposing you can't pull with 100 newtons, okay, why don't we do this? We have it fixed at the top, and it goes round a pulley wheel, like that. 100 newtons, okay, and we pull up on that one. But look, the pulley wheel has got an upwards pull on this side and an upward pull on that side. Those two have to add together to make 100 newtons, so therefore you only have to pull 50 newtons. Isn't that clever? And of course, if you had an extra one, like this, so that you've got your weight hanging on here, 100 newtons, and the string went up and down and up again to be fastened on the bottom of that, then basically you only need a third of 100 newtons to pull it. We're now going to talk about the force that pushes you out when something is going round and round in a circle. You've heard it on the radio, you've seen it on telly. It's called centrifugal force, isn't it? If it is a sock in a spin dryer going round and round, it's not pushed outwards. It tries to go in a straight line until it's hit by the wall, and the wall pushes it inwards. A conker on a string. I should have a real one for this for a demonstration, shouldn't I? But it's not September, so there's no conkers around. A conker on a string, it only goes in a circle because you're pulling the string. If you let go of the string, it goes all over the place. Here's an animation of a satellite going round the Earth. V represents its velocity, which is the speed in any given direction, and you can see that keeps changing because it's a circle. And A is acceleration caused by force. Believe it or not, it's accelerating towards the Earth all the time, but because it's going at just the right speed, it never actually hits the Earth. But look, the acceleration and hence the force are directly towards the Earth, towards the centre of motion, and that's because gravity is causing that force. It's beginning to get dark. Spooky, isn't it? And I'm going to show you definitely that things need to be pulled towards the centre if they're going to go in a circle, and if they fall off it, they fly off in a straight line at a tangent. And what I've got is a sparkler on my drill here, and the sparkly bit is going to go around in a circle because it's pulled in by this piece of metal, and all the bits that come off will actually go off at tangents. You watch and wait. So as the burn bit goes round and round in a circle, the sparks all fly off in straight lines at a tangent. They're not thrown outwards, they go off in straight lines. Now here's a picture of spacemen in 0G, isn't it? They're floating relative to each other, apparently weightless. But no, it's not 0G. Of course there's gravity there. That's what's keeping the spaceship and them going in orbit. They are not weightless. They have a weight because it's the pull of gravity. The thing is that they are accelerating towards the Earth at the same rate as the space station is. So therefore, between them, they feel very little difference. This is the simulation that's done inside a special aeroplane they call the Vomit Comet. And people feel weightless, in inverted commas, but the aeroplane has to fly a special path, a bit like if you throw a stone. It's called a parabola. And so the aeroplane goes up, over the top and down again, and for all that time the people inside are accelerating towards the earth at the same rate as the aircraft, and therefore they feel, relative to the aircraft, no forces. They call it weightless, but it certainly isn't. I'm going to try and simulate that, but first of all you've got to remember Galileo's famous experiment. He said that when you drop two things together, and if there's not too much air resistance, they accelerate at the same rate. So watch this. Now, what we're going to do now is do the aeroplane. So this is the aeroplane, and this is the man inside it, or the lady inside it, okay? And what I want you to do, I'm going to throw it like a projectile, and you've got to try and ignore the background and just watch these two and see how they seem to float relative to each other. I'm now going to finish up by talking about pressure. Now, pressure is what makes holes in things and what cuts things. Not just force to do that, but pressure. Pressure is calculated, I know you don't like sums, by the force divided by the area. In other words, you get more pressure if either there's a bigger force or a smaller area. For example, if you wanted to cut a cake, if you use this rule, like that, it wouldn't cut it very well. But if you use a knife with the same force, because it's got a small area, it cuts it better. Here's a few other looks at pressure. If you wanted to push a drawing pin into a piece of wood, I think I know which way round of these two pictures you'd do it. Well, in both the pictures, the force is the same at both ends of the drawing pin, but where there's a point, that's a small area, so therefore a big pressure, and that's the one that makes the dent. A truck vehicle is exactly the opposite. It's heavy, so it needs very large area in contact with the ground, which makes less pressure, so it doesn't sink into snow or muddy ground. And skis do exactly the same thing for you. If you stand on soft snow, without skis you sink into it, but with skis you don't. Now I want to tell you about air pressure. Now, air molecules are moving around us all the time and bashing into us and stuff like that. And that actually puts a lot of pressure on us. In fact, far more than you think. If you see this table here, there we are, the surface area of that was about a metre squared. And so the pressure that the air puts on that is the equivalent of 100,000 apples sitting on top of it. How about that? Or maybe 100 London buses. So it's a huge pressure. And I'm going to give you a demonstration just to show you how much that atmospheric pressure really is. I'm going to use a can of Pepsi. Okay, empty can of Pepsi. I'm going to drink it first when you're not looking. And what I'm going to do is put a little bit of water in the bottom, bring it to the boil, and so that water is going to expel all the air from inside there. So basically the only thing that will be inside there will be water vapour. And if I plunge it upside down into some water, then no air can get in, so there's no air whatsoever there at all. The water vapour inside will condense back into water again, and so the air pressure is the only thing pushing on it. Have a look and see what happens. Well, the water inside is boiling away. You might be able to see some steam coming out of there. So what I'm going to do, the steam has now pushed all the air out, which means that there's absolutely no air in there. And when I put this into the water on the right hand side, no air can get in, so there'll be no air in there whatsoever. So the air pressure can do what it wants. Watch carefully. There. That shows you how big air pressure is. Squashed. Completely flat. Yeah, well that will do for this one, won't it? But before I go, I'm just going to leave you with a photograph of an impossible triangle, which I actually made. Photograph, here it is. Here is Pam holding my creation, which I made from 3 pieces of wood, as you can see, but look at the corners. It's just not possible. But I made it possible. Don't worry, the solution is to follow. And here we are, this is how I did it. Sorry to be such a cheat, but it's the only way. Thank you for watching. Bye everybody.